So one thing to add, at 9:15, we have a primary session on making a moon lander. But if you stick around with us now, we have Dr Orson Sutherland with us, who is the Mars Exploration Group leader at the European Space Agency. So stick around, because this is all about the future of human spaceflight and robotic exploration.
See, when I was at school, no one told me that that job title existed.
I know. So
you know, the fact that you can go and do that, be in charge of robotic exploration on Mars is pretty good. Dr. Sutherland, can you hear us?
I can hear you. Can you hear me?
Yeah.
Loud and clear.
Hi.
That's lovely. Thank you very much for stopping by for Mars Day. We've got a lot of people watching, and a lot of people are very grateful that you've stopped by. Just tell us a little bit about where you are and your extraordinary job title.
So good morning, everybody. Good morning, UK and around the world. I'm in the Netherlands in a place called Noordwijk at the European Space Technology Centre, which is the biggest of our sites, but we have many sites around Europe.
Fantastic. Wow. And what do you do if you were to sum up your job at a dinner party, for example? You had to sum up what you do for a living. What do you tell people?
Okay, well, I think I have one of the best jobs in the world, for starters. We get to dream up what missions Europe should be doing on Mars. We get to think about how we would actually turn those into real projects, and then we get to implement them. And we get to use very clever people all around Europe in our industries to build the spacecraft, the rovers, the launchers, and all the bits and pieces that we need in order to do science on Mars, and maybe even one day to bring humans to Mars.
Amazing.
Oh, it's so cool. So as we've been saying, we'll leave you to do your presentation in a moment, but everyone else, there will be questions at the end. So get in that chat, leave those questions, and we can put them to Orson at the end of this.
Orson, it's all yours.
Looking forward to it.
It's all yours. The
Thank you very much. Okay, so what we've just shown you is a video of the Mars sample return mission. It's going to be an extraordinary historic mission. It's the first time that humans will fly to Mars, to the surface of Mars, and then return. Now, it won't be with humans this time. It will be with robots and robotic systems, but it will be the precursor for human missions to Mars. And we want to show that the technologies that you need in order to be able to fly to Mars and come back work, and that we can make all those systems interact properly. What you've seen there, in fact, is an amazing relay race between 3 different flight systems. So the first one was a rover, the Perseverance rover, and Perseverance rover is on the surface of Mars doing great science today. It's preparing those little tubes that you saw through the video for collection. And then it brings it back to that lander, and that lander will launch sometime in the late part of this decade or early part of the 30s and land on the surface of Mars. And on that lander, there is a small rocket. And in the nose of that rocket, there is a ball about the size of a football. So think of a football, and that's the size it is. And at this point, it's in 2 halves. And we're inserting those little tubes with a special robotic arm into the ball. The ball is then closed up, sealed up. The nose cone of the launch is closed up, and then we fire the rocket into orbit around Mars. It's orbiting Mars at this point at roughly about 400 kilometers above the surface. And it's a rocket that has two stages. We separate the upper stage, and then eventually the ball is pushed out from the upper stage and starts orbiting by itself. And at this point, the European Space Agency's Earth Return Orbiter has flown to Mars, is now in orbit around Mars at roughly the same altitude, and is looking for that ball. Imagine that. We're looking for this tiny ball orbiting around Mars. It's like, if you can imagine being on the top of the Tower of Pisa in Italy, and you had a camera that was strong enough to look at Big Ben, it'd be like reading the time on the Big Ben from the Tower of Pisa in Italy. So that's the challenge. And then we find the ball, and once we've found it, we watch it for a while to work out exactly what its orbit is, and then we fly up to it and we catch it. And once we've caught it, we have a series of robotic systems inside the payload, which put that little ball into what we call the Earth entry system. We fly back home, we fly back to the Earth. And when we're roughly 3 days away from the Earth, we release the Earth entry system into the Earth atmosphere, and it lands safely in the Utah desert in the US. And at that point, there's a fourth stage that comes. Thank you very much. There's a fourth stage that happens where they collect the entry system, and they bring it back to a special facility where they process those tubes, and the scientists get to do their work on it. And you have to think a little bit about it, a little bit like it's the Apollo missions. We were bringing all these samples back, and can you believe that they are still doing amazing science on the Apollo samples today? And that's what this is going to represent, but for Mars. We're going to be doing decades and decades of amazing science on those samples. Anyway, so having talked you through the video, I'm going to kick off with my presentation. And so the presentation is about the European Space Agency's exploration program. Now, throughout the presentation, I will probably say ESA. ESA is short for European Space Agency, it means the same thing. And ESA consists of 22 member states, okay? There's 22 member states. But when we add all the associated and cooperating agencies and states, that makes 31 countries that are working together to provide access to space for Europe, which includes the UK. UK is a very important part of ESA. It's one of the so-called Big Four, together with Germany, France, and Italy. Now, ESA exists because together and through partnership, we can achieve more, we can do more. Some projects are just too big for one nation alone. Even America, with all of its might and all of its wealth, and NASA and all the wonderful things that it does, it still looks to its international partners to do really big things, like the International Space Station and like the future Artemis program to return humans to the moon. So when I talk about Europe's space program, I want you to rest assured that I'm talking about the UK as well, and that the UK is playing a major role in that. Next slide, please. So why should we do space at all? You know, some of you might be asking that question. Now, the nerds in the crowd here are probably going to say because it's cool, because it's like science fiction, because there's spaceships and there's rockets, and it just looks so much fun. And then the adventurers are going to say, well, because it's probably the biggest adventure you can go on. It's going to be the funnest thing that a human can do. And the scientists will say, because there's just so much to learn. There's so much we don't know about the solar system and the universe, and we want to learn and discover. Personally, I think it's all of those things. It's an amazing adventure of discovery, and we will discover amazing things about our solar system, the very nature of the universe. And maybe just as importantly, we'll learn a lot about ourselves, humans, and humanity. Are we alone in the universe? How did life start? Are there other intelligent life forms out there? But to achieve these goals, we need to get smarter. We need to be more knowledgeable. And therefore, we need to strengthen our STEM research, which is the first of the pillars there on the page. We need to make sure that there are exciting jobs waiting for you, the next generation, so that you can bring your passion and creativity and skills to your careers, hopefully in space. And we will also need to keep cooperating with international partners, whether that's within the 31 countries of ESA or beyond, to the US, to Japan, India, and many others around the world, because together we can do more. And maybe, just maybe, by working together, we can help to make our home planet a more peaceful home. Next slide, please. Space exploration, though, it's not just about rockets and aerospace. It's definitely that, but it's also so many other things. It's about growing things in space. I literally mean growing plants, understanding how the human body reacts and adapts to life in space. It's about closed cycle waste and water processing. Now, take this away. An astronaut actually has to drink his own wee or the wee of the people on board, right? And I'm not joking. Okay. I mean, it's filtered, of course, and you won't be able to tell, but yes, your morning cup of tea or coffee is brewed from last night's pee. Now, when you think about space, I want you to think of the full breadth of human science and technology. Of course, we want to go to new places and we want to discover the origins of life and understand how our solar system came to be. But in order for humans to do that, we're going to need more than just robots and spaceships. We're also going to need to understand how humans can survive for long periods of time in microgravity or low gravity, such as on the moon or Mars. We need to understand how radiation will affect not just the human body, but the plants we'll have to grow to eat, and maybe the pets we'll bring along for company. Because space is about biology, it's about psychology, it's about medicine. Because as exciting as traveling to the moon and Mars or an asteroid might seem, there are long periods of time where you're in the darkness of space, isolation, and maybe even loneliness. And all of that research is relevant to the Earth, to our medical systems, to climate change, to psychology, to aged care, caring about our aged people. So on this slide here, you can see some of the examples. ESA is building a database of success stories. And of how our space effort is benefiting life on the Earth. These are just some examples, but we have many, many more on our website, and I would encourage you to go and look how space is helping better life on the Earth. Next slide, please. Now, I like to think about ESA's exploration of the solar system a little bit like a metro or a tube map. In 2014, we had some exciting flight systems in operation and under development. But it looks pretty empty, right? This tube map. It's a little bit like, I guess, when we had the first tube line in London in 1863. It was amazing. It was paradigm shifting. Goodness gracious, we were traveling underground in trains. It was amazing, but it was just the beginning. And as you all know, today, the metro and the tube maps of all the major cities around the world are very, very dense. Now, at that time, we'd built 5 ATVs, automatic transfer vehicles, to resupply the International Space Station. We'd started to develop the European Service Module and the Rosalind Franklin Rover. We were operating the Trace Gas Orbiter and the Mars Express spacecraft around Mars. And we were just doing amazing science and beginning to increase Europe's reach out into the solar system. Next slide. By 2024, though, this year, the solar system tube map looks like this. It's grown tenfold, and it's still growing. Now, granted, not every mission depicted on this map is operational today, but they are in development and will be operational around the end of the decade. ESA has the Bepi-Colombo mission flying to Mercury. We have the JUICE mission flying out to the Jupiter icy moon system. We still have Trace Gas Orbiter doing great science out at Mars and Mars Express. But Trace Gas Orbiter today is also the main communication relay between the surface of Mars and the Earth. It's channeling data for NASA's rovers and even China's rover. ESA's European Service Module has helped the first Orion mission to fly around the moon, the first in a series of so-called Artemis missions, aiming to send humans back to the surface of the moon. That'll be the first time since the Apollo 17 crew walked on the surface of the moon in 1972, more than 50 years ago. But ESA is not stopping there. We're also working with NASA and the Japanese Space Agency and others to develop an outpost for humanity in cislunar orbit. That's an orbit around the moon. And the outpost is called the Lunar Gateway. Astronauts will spend time on the gateway and make trips down to the lunar surface and back. Now, to support surface missions, ESA is also developing its very own lunar lander called Argonaut, which will bring rovers, power and communication systems, and potentially also machines for building a lunar base down on the surface. To provide round-the-clock communications with the Earth, both from the surface of the moon and from orbit, we are developing a communication and navigation constellation around the moon called Moonlight. And we're also studying a similar system for Mars called Marconi. So that humanity can avoid the fate of the dinosaurs, ESA is developing systems to detect and stop near-Earth objects, so-called NEOs, from impacting the Earth. We are literally developing satellites that will push NEOs off their dangerous orbit to a safer one, keeping humanity and the rest of life on Earth safe. We are flying out to comets and to asteroids with missions like Comet Interceptor and Hera, and the Mars sample return, as we saw at the beginning of the presentation, will make the first round trip to Mars, setting the scene for future human missions to Mars. Next slide, please. So this is the International Space Station. It's humanity's closest space base. It's like a big science laboratory flying around Earth. It orbits our planet at an altitude of 400 kilometers, making one revolution every 90 minutes at a speed of, get this, 28,000 kilometers per hour. The ISS, the International Space Station, was built by countries from all over the world working together, including the United States, Russia, Japan, and many European countries, including the UK. This shows how countries can collaborate on big projects, even if they compete in other areas. Building the ISS was like a giant space puzzle or a big Lego kit. The first piece was sent up in 1998. Think about that. That was 26 years ago. And since then, many other pieces have been added to make it as big as it is today. Now, it's so large that it's like a house with 5 bedrooms. It even has its own solar panels to generate power, just like solar panels on your houses on Earth. Astronauts from 21 different countries have lived on the ISS, doing all sorts of experiments that can only be done in space. They study things like how plants grow in space, what happens to the human body when you're living without gravity, and even how different materials behave in space. This helps scientists learn a lot about how to do things better in space, but also, and very importantly, how to make life better on Earth. On average, there are 7 astronauts on board at any given time, but the record is 13 at the same time. One cool thing about the ISS is that it's all about sharing and learning together. Countries share their space knowledge and technology, and even though the ISS will one day be retired, the lessons learned from it will help with future space missions like Lunar Gateway and future human missions to Mars. So the ISS is not just the space station. It's a symbol of international cooperation, a unique science laboratory, and a stepping stone for future space exploration. Next slide, please. The next step for humans is the Lunar Gateway. It's humanity's space base that will orbit the moon. It will be 400,000 kilometers away from the Earth. It's part of NASA's Artemis program, and it's aiming to return humans to the moon and eventually take us on to Mars. The Gateway will be a place where astronauts can live, work, and prepare for missions on the surface of the moon and even deeper into space. Building the Lunar Gateway is another big team project involving countries from all around the world: the United States, the European Space Agency, and therefore the UK, the Japanese Space Agency, and the Canadian Space Agency. They're all working together, and each country is contributing different parts, like living quarters, scientific labs, and even a robotic arm to help with tasks outside the station. The Lunar Gateway will orbit the moon in a very special way. It will follow a path that allows it to stay in constant communication with Earth and have easy access to the moon's surface. This orbit has a very difficult name to pronounce, but I'll say it anyway. It's called a near rectilinear halo orbit. The way to think about it is it's a little bit like a dance around the moon. It gets close and then it moves away, but it's always staying connected. It will oscillate between about 1,000 and 70,000 kilometers from the surface of the moon. And one of the coolest things about the Lunar Gateway is how it will help us to learn more about living and working in space. It will be a place to test new technologies, study the moon up close, and figure out how to keep astronauts healthy during long space missions. This knowledge will be super important for the future adventures to Mars and beyond. The Lunar Gateway is smaller than the International Space Station, but it's still pretty big. It will have space for up to 4 astronauts to live, and they'll be able to live and work on the station for between 30 and 90 days at a time, and it will have an absolutely amazing view of the moon. Next slide, please. Space isn't just about the thrill of exploring the unknown, though. It's also about facing some very unique challenges that astronauts must overcome. First of all, microgravity. Imagine floating around where up and down don't mean much anymore. Sounds fun, right? But in space, this can make simple tasks very tricky, and it affects the astronauts' muscles and bones. Astronauts also have to deal with radiation. Space is filled with invisible rays that can be harmful. A little bit like if you get too much sun, right, on the Earth. But here it's even more intense. That's why astronauts need special protection to stay safe. Then there's isolation, being far from home, away from family and friends. That can be tough, even for astronauts. Astronauts spend months at a time with only very few people for company, which means they have to get along really well and support each other. Now, even though you can see the Earth from the ISS and what a magnificent view it is, astronauts are still pretty far from the surface of the Earth, and help is rather far away. If something goes wrong, astronauts can't just call a repairman or pop into the hospital. They need to be prepared for anything, which requires a lot of training and bravery. Lastly, astronauts live in closed environments. It's like a big house, but just imagine not being able to leave that house whenever you want. A spacecraft like the ISS is like a tiny sealed home where everything must be recycled and reused: air, water, everything. And so while astronauts are real-life superheroes, they face challenges that require not just physical strength, but also mental toughness and teamwork. It's definitely not for everybody. But who knows, maybe one of you in the crowd here will be a part of the next generation of space explorers that are ready to take on these challenges. You will certainly have learned a lot more by the time you're ready to fly into space. Next slide, please. So let's zoom in just very quickly on a few more astonishing changes that the human body goes through when you're in space. The journey inside the astronaut's body reveals just how adaptable and yet how vulnerable humans are in the vastness of space. You might be surprised to learn that in space, without gravity pulling us down, our brain and the fluids shift upwards. And this can feel like you've got a constant headache or a head cold, and can even change the way our brains work and how we move. We have to learn how to rebalance ourselves and coordinate ourselves in space. Our eyes have to adjust to a whole new view. The same shift that affects the brain can also squish our eyeballs a bit, altering our vision. Some astronauts come back from space with their eyesight permanently changed. They have to wear glasses when they didn't before. In the weightlessness of space, muscles don't even have to work that hard. Sounds relaxing, right? But it's actually a big challenge because muscles can weaken and shrink, or what we call atrophy, without regular exercise. Astronauts have to work out for 2 hours every day just to keep their muscles strong enough for when they come back to the Earth. Imagine that. In the silent expanse of space, our bodies tell us loud and clear how much we are built for life on Earth. From our brains to our eyes to our muscles, every part of us has to adapt to the new rules of living in space and microgravity. And through this incredible journey, we learn not just about the limits of human exploration, but also about the resilience and adaptability of the human body. Now, at ESA, we want space to be for everybody. And that is why John McFall is training to be a para-astronaut. And as I'm sure that you know, John is a para-Olympian, a medical doctor, and just a generally amazing guy. And he is helping us to understand the challenges of life in space for an amputee. A truly amazing fellow. You can see some pictures here of his training for that on the slide. So next slide, please. Now, to finish up, I want to talk briefly about the destination that I work on, the thing that inspires me, that gets me jumping out of bed every day: Mars. Now, imagine a world where we can step onto another planet, a place so different yet so connected to our own, a place where one day humans may live and thrive. At ESA, we want to turn this vision into missions for the future for humans, that one day humans can work on Mars. But why Mars, you might wonder? Well, Mars is our closest neighbor that offers the best chance to learn more about our solar system, the origins of life, and possibly about the future of our home planet. Mars is like a time capsule, holding secrets about the solar system's past, and maybe even clues to life beyond Earth. ESA's missions, like Mars Express and the upcoming Rosalind Franklin mission that you can see here on the screen, are paving the way by studying the planet's atmosphere, the surface, and its subsurface. They're looking for signs of water and life, testing new technologies for landing, and figuring out how to use Mars's resources for a sustained human presence on the surface. But going to Mars isn't just about the science, it's about the challenge. Humans going to Mars will have to travel further and stay longer than we've ever done before. They'll face isolation, radiation, and the unknown. But overcoming these challenges pushes us to innovate, to create new technologies that not only help us explore space, but also to improve life on Earth. ESA's vision is bold. We want to send Europeans to Mars by 2040, using robots as scouts, like Rosalind Franklin, and building the technologies we need for a sustainable presence on the red planet. It's not just about landing on Mars, it's about exploring, learning, and coming back safely with answers to some of our biggest questions. This mission to Mars is more than adventure. It's a step towards understanding our place in the universe. So I say, let's dream big, let's stay curious, and support the journey to Mars. I think it is a safe bet that more than one of you will be working on our missions to make this dream come true. And who knows, there might even be one of you in the crowd here who might be lucky enough to step foot on the red planet one day. And with that, I'll fast forward to 2 slides down, please. And I'd like to thank everybody here this morning for listening in on this talk. I hope you found it interesting. There are some web links on this page here, which I'm sure the friendly people at UK STEM can make available to you. I hope you'll enjoy them. They talk a lot about our Mars missions and exploration in general. But for now, humans, goodbye, and don't stop exploring.
Oh, thank you so much, Orson. That was brilliant. I mean, I really hope someone in this group watching right now is going to become an astronaut. We need them. We need them.
Orson, I feel inspired. Just that last bit you were talking about there, about dreaming big. I was transported back to Rice Stadium, 1961. John F. Kennedy saying, "We choose to go to the moon in this decade."
Right.
Stirring stuff. There is just something really inspiring and stirring about these kind of grand space missions, isn't it?
Absolutely.
Being human when we're sort of faced with such incredible opportunities and ideas, it just gets you going.
It does.
Absolutely.
And we've got some questions from some schools.
Yes, we do. We've got hundreds of questions. So please stay there for the next 5 hours.
Yeah. No, but let's choose one.
Very happy to. Can talk about Mars all day.
Well, this is the thing. We could just talk about Mars all day as well, but we've got to be disciplined.
We've got one question,
Okay.
and that's
That's right.
from St. Joseph's Primary School, which is, how long will it take to get to Mars?
Crikey. That's a question.
That's a very good question, very pertinent,
Yeah.
and it depends is the answer. It depends what you want to do there. If you're going with robots, like a rover, you could be there in 9 months. If you want to take a little bit more because you have to take heavier payloads, it might take you somewhere between 12 and 24 months, so that's 1 to 2 years. But if you want to bring humans there, I suspect that we're going to be taking more than a year to do that because we want to be safe, make sure that the humans can land on the surface safely. There'll be a whole bunch of checkouts.
That's an interesting one because when we think about the moon's always roughly the same distance away from the Earth. But of course, Mars isn't. It's a bit like being on a running track. It's on a different, so it can be on different sides of the sun, and it can be quite close, and then it can be far away. So it depends. It's a much more difficult thing to get to Mars than the moon, presumably.
Absolutely. In fact, we wouldn't even go. You can't even go any month you choose. You basically can go once every 2 years, and then in a very precise window of roughly a month. So yeah, it's a challenge.
Well, thank you so much, Orson. We've really loved speaking with you today, so thank you so much for joining us for Mars
super
Day.
pleasure.
Thank you very much. We could stay all day, and thank you for a perfect talk. It was beautiful and brilliant, and a pleasure. Thank you.